I have 7:30. And we're going to continue chapter 3. So last time we talked about the different classes of ISAs. And today we're going to get started on MIPS. So MIPS, as I mentioned throughout this course, we're going to use it as our example ISA. And we will only be going into the details of MIPS, but a lot of the principles are the same across the board. And MIPS is used in a large share of the embedded core market. So lots of consumer electronics that are in embedded systems use MIPS. Network and storage equipment, cameras, printers. And MIPS is also a representative ISA of modern ISAs. So the different components that go into the ISA are going to be what kind of storage is available. Is it registers? Is it memory location? Is it only memory location? Things like that. But for MIPS, you have registers and you have. And then what are the possible set of operations? Can you do AND, can you do bitwise AND, can you subtract, divide, things like that. And then for those possible set of instructions, what are the different formats that you're expecting? So what are the sizes of the instructions? How many different fields go into an instruction? And what are the sizes of the types in the instruction? Right. We're going to start with the storage cells. So MIPS registers, it's a 32 by 32 register file. So every register is 32 bits wide, and there's 32 of them. So you can access it 0 through 31. And a 32-bit string of data, we're just going to call it a word. So 4 bytes of data is 1. And not all 32 of these registers are usable by the user. Like register 0 is always hardwired to be strictly 0. And register 1 is reserved for the assembler. And then there are different names for different types of registers as well. So the ones that start with T are for temporary variables. And the ones with S are for saved variables. And here is like a summary of the different registers. So like I mentioned, 0 is 0. 1 is reserved for the assembler. These are for your returns. So your function return. And this is your function arguments. So like when you make a function and it has the inputs, that's what these are for. And then your temporary registers are like your local variables that get created and consumed within the function. And then you also have saved temporary. And then you have more temporary registers after those. And these are reserved for the operating system. And then you have these other system variables like the stack pointer, the frame pointer, and then we have the return address for calling procedures. So the memory organization is used for your data, like arrays, structures, and just other dynamic variables. And to apply any arithmetic operations to your stored data, you need to first load the values from memory into the registers, not directly work with the data from memory, right? We're a load store architecture. And if you want to store what you did to that data back into memory, you can store the result from the register. And the memory organization is basically this very, very large single dimension array with these addresses. And the addresses we're working with are typically going to be byte addresses. So that means that the first address points to the first byte of data or first 8 bits of data. Second is the second 8 bits, second bytes. And if we're talking about words, a word is 4 bytes of data, right? And most of the time, even though our memory is byte addressable, we will be loading by or trying to access by words. So you'll see that we increment by 4 a lot of the time. Like instructions are 1 word, right? So when you increment the PC address, which points to the current instruction, you're always incrementing it by 4. And if you're looping through an array, you're going to, again, increment it by 4. Because when you load something in, a register is 32 bits, it's going to load the word that it's pointing to. So you'll often also see word addresses. So byte address, 1, 2, 3, 4 bytes. That's the first word address. But again, you'll often see it as byte addresses and incrementing by 4, not word addresses incrementing by 1. Right. So, like I mentioned, most data types that we're using in MIPS are words. So we're going to be incrementing by 4. And one thing that is very useful for us is that we want to keep our data word aligned. So this is an example of our data being word aligned. Like if this is the first byte, then 1, 2, 3, 4 bytes makes 1 word, and the next one would be right after it, right? But if a word starts at 1 instead of 0, then we're not quite aligned. Okay. Then the same thing if we're at 2, we're like 50% in this word, 50% in this word. We want to stay word aligned so that we can just keep accessing by multiples of 4. Does this make sense to you guys? All right. So one key thing that we should always remember is that registers are much faster to access than memory. And in order to operate on memory data, we need to load those memory data into our register file. So this requires a few more instructions to be executed rather than having instructions that directly modify or use memory as an operand. And the compiler must use registers for variables as much as possible, rather than trying to go back and forth from memory. So this register optimization is important because registers are much faster than memory. So you just want to load a few things, work on them in the register file, and then when you're done, put them back into memory. You don't want to have to keep going back and forth. So here's our example. So this is the CPU. You're going to have this control unit. Here's our registers. And the PC is another register. Right? And this is our instruction. And we have what is shown as the data path for now, just a simple ALU. So an ALU is just something that is going to implement many different functions. And based on the operation code that you give it, it'll do something like add, subtract, things like that. Then we have the address in memory that we want to access, as well as the data to get that memory to and from memory. So one thing that we might want to keep in mind with MIPS and ISAs in general is that immediate operands are used quite frequently. Okay, so small constants like indexing your array, or it could just be one small magic number that you need in your code, right? I just need to increment this by 5. So 50% of operands do this. So because of that, we don't want to have to first load them into memory and then read them from memory. So we can, one is this hardwired register for 0, right? But the other way is we allow using an immediate operand to avoid this load instruction. Because memory is, again, about 100 times slower than the CPU. So if you can remove this load instruction that could cost you 100 cycles of stalling, you'll want to do it with it. So here are different instruction formats that we're going to focus on. So the first is R-type. So these are ALU instructions. This is mostly going to be like your add, subtract, things like that. Bitwise and, bitwise or. Your opcode is going to tell you what format your instruction is, as well as for the different instructions, different types like I type and J type. It will also tell you what the operation is. But for R type, the opcode will tell you that it's R type, and then the funct code will tell you what is the actual operation. And then you have 3 operands for R types, RS, RT. These are the ones that you're going to work on. RD is your destination. And then shamped is for if you're doing a shift function. It's just the amount that you're going to shift by. And then I types, you can see we also have the opcode, and the opcode will tell you if you're a branch not equal, branch equal, load, store, or add immediate, sub immediate, things like that. You have 2 register operands. In this case, one of these RT, actually, yes.
You said that RD was a destination.
Yes.
I thought RS was the source variable and RT and RD were the operands.
No, RT is the destination. And sometimes RT is the destination. Like I types, not all I types have a destination, but a load word has a destination, right? Because you're loading from memory into the register file. So RT could also be a destination register. But RS, RT are your operands. For R type, RD, it's easiest to remember because it's the destination. And you also don't have to remember this because for exams and everything, you'll have the MIPS reference sheet. And you can see the MIPS reference sheet on campus in the files. So you'll know exactly what you don't need to memorize, but what you should do is get familiar with the MIPS reference sheet so you're not spending too much time during the 50-minute exam looking through it. Okay, so as I mentioned, so I type, this is where you're going to need this immediate. It's 16 bits. It gets sign extended, right? So this is your add immediate, how you can do something like this, just add. It also gives you your offsets in order to do load word, store word. Because one of these registers, RS, is your base address that you're trying to point to in memory, and then you have this available offset. So you can kind of have more complex instructions. You don't always have to modify that base address. And then jump is like a branch not equal, branch equal, but there's no condition. So you're just always going to jump to this different instruction that is not just PC flexible.
So you use jump to like exit programs.
There's a few ways that you can use the jump, but one way is there's a different instruction for exiting a program. But usually jump is used when branch equal, branch not equal, with this 16 bits immediate is not far enough, right? Because you have 32 bits of space in the memory to point to. But if I only have 16 bits in my immediate, if I'm at the bottom of memory and my destination is at the top, I cannot reach it. So the instruction sets. So one reason that we have assembly language versus machine language is, although it's still difficult to read and understand, right? Like if you're given a function in assembly, like in the homework, it takes some time to figure out what exactly it's doing. And it would be much easier if it was in the high-level programming language, right? But assembly is still much easier than looking at machine code, right? So rather than looking at something like this, we can look at add RDRs, where these are substituted with register numbers. And assembly can also provide these pseudo instructions that are also much easier to exist. So this move T0 to T1 does not exist in reality, but it is much easier to understand at the program level what it's doing if you're calling it move T0 T1 rather than add T0's destination. T1 is one of the operands, 0 is the other operand. So it's basically just T1 plus 0 into T0, right? And that is essentially move T1 into T0. But because we don't want to kind of waste our finite set of instructions, because we only have 32 bits, this move instruction doesn't really exist. But we can say that in the assembly language, this is just this instruction. And also these pseudo instructions can be turned into like multiple instructions if they need to. So when you're considering performance, you should count the real instructions, not all of these pseudo assembly instructions. All right, so for our instruction types, we have data operations. So arithmetic, that's your add, sub, add immediate, and then we have logical, bitwise and, or, nor, shift left logical, shift right logical, and immediate or immediate. We also have data transfers. So this is load from instruction. And then we have memory instructions. So load word, store word. And then we have sequencing. So our control instructions. Conditional branches, branch if two registers are equal, branch if two registers are not equal. Unconditional jump, and then we have jump and link. And then jump register is what we're using to exit from programs. So there's also set on less than immediate. These are often used in conjunction with branch equal, branch not equal. So arithmetic instructions. So all ALU instructions have 3 operands, 2 sources and 1 destination. And so because of this, we have this same form, and we always have destination first. So here, add RD, RS, RT, and you'll see this on your MIPS reference sheets. So this is why you wouldn't need to memorize that RD is the destination, RS and RT are the operands, because you can see it here, right? Same thing with sub. It's in this fixed format because of our design principle. That's we like regularity. Okay? Very simple because with simplicity, we can have better performance at the hardware level. Right. So here's some high-level C code, right? We have F, and we want it to be G plus H and then minus I plus J. So we have all the different variables, and they're gonna go into these different registers. So F, G, H, I, J into S0 through S4. The MIPS code for this would be add into T0, so our temporary, S1 and S2. So S1 and S2 are G and H, right? So G plus H is basically this temporary register. Add into T1, S3, S4, that's I and J, right? So now we have G plus H in T0, I plus J in T1. And then to do the final operation, sub into S0 because F is S0, right? T0, T1, because this is T0 and then minus T1 into S0. So for R types, these operands must be registers, right? But that is just for R types. I types, the three operands, one of them is going to be an immediate. The other principle that we have is that smaller is faster. So here is our model that we went over last time. And we have kind of like a short animation on how this is going to work. Right, so we have PC at address 0. It's going to fetch the first word here, right? Which is essentially add R31, R0, R1. So that's going to be moved from main memory into our instruction register. And now that it's in our instruction register, we can figure out that we need to read from the register file R0 and R1, right? So R0 is here, R1 here. Tell the ALU to do this add. So we'll get 6 back out of here, right? And store it into R31. So now R31 becomes 6. And then we would increment PC by 4. Because if we just incremented by 1, we're still getting part of that add instruction. So we need to increment by 4. We get the next word, and we're saying it's this sub, and sub R1, R31, R2. In this case, we grab R2 and grab R31. So this is actually R31. This is R2. And we're going to subtract. And we should get 2 back, right? And it goes into R1. So with the 2 instructions, we basically moved R1 into R31. And then we replaced R1 with the R1 previous value minus R2. Okay. So the other thing that we always want to keep in mind is from Amdahl's law, right? That we learned about. We want to make the common case fast. So small constants are used quite frequently in MIPS instructions. So we create this immediate operand to avoid the load instruction. If immediates were not used very often, like maybe 5% of the time, maybe it's not worth optimizing it by making an immediate instruction for it. So here's our add immediate. So RT is the destination in this case, because we have no RD, right? And the reason that we use RS and RT is so that we have that same instruction familiarity, right? It's very similar. And then we just have the immediate. Again, you don't need to memorize this. This is on your sheet. Here's our example. Add immediates. S0, 0, 4. So basically S0 plus 4 back into S0. So there's no subtract immediate instruction. This is just an optimization because if we just use a negative constant, add a negative number is subtraction, right? We also have these logical operations. So we have bitwise and immediate, or immediate, nor, and then we have shifting. So here's our bitwise and this is sometimes useful to mask bits in a word. So we just want to select some bits and clear the others to 0. So if you want to clear them, you just make sure that your mask is zeroed and the ones that you want to clear, and 1's where you want to save value. And again, this is an R type. So we have RD, RS, RT. And we also have I type, where RT is the destination, RS is one of them, and then we have this 0 extended immediates. So here's our example. So and T0, S1, S2. So S1 is this, S2 is this. We take the and between them. We get that it becomes 0 everywhere except for these two values, these two bits. So that's our result. We can also do bitwise or. Yeah. Here's our example, or T0, S1, S2. We have the same example, right? Now, wherever there's a 1 across either of them, it moves down into T0. And we also have nor. So nor is just, we take the or and complements, right? So what we had before, but now we also flip everything. Right. So we do not have a not instruction in MIPS. And that is simply because you don't need one, right? Because if you just do this instead, you get not. So you can just do a nor 0. And that would invert a. So you do the nor instruction, use 0 as the second operand, and now you get an invert. So there's no need to, again, waste our different combinations of instructions to create not if we have nor already. And we can just use that fixed register 0. But what could be useful, again, is having maybe a pseudo instruction for the assembly language that allows you to do not. But really, it just becomes this nor with 0 as one of the operations. All right. So shift logical. So this is going to shift left or right and fill anything that is coming in with 0s. So is a R type, and we have RD is the destination, RT is the register to be shifted, and we don't use RS. We're using shan't, which is our shift amount. And we have shift right logical as well. So if we shift left, we basically are multiplying, right? So if we shift left by 2, we're multiplying by 4. If we shift left by 3, we're multiplying by 8. But that's not always the case, right? If we're shifting out zeros, then yes, it's the case. But if we're shifting out ones, then our number is most likely going to be kind of small. Okay. And then shift right is going to divide. And again, you aren't going to get like decimal points out of this. So if you're shifting out a 1, it's not going to become a 0.5. It's just going to be truncated. Okay. So here's our example. Shift left logical, T0, S1, 2. So we're going to shift S1 to the left by 2, which is multiplying it by 4, assuming we don't have any 1s out here, but we do. So it's not a multiply by 4. So everything gets shifted to the left by 2, and anything that is coming in is just zeros. And you can see that this is not a multiply by 4 because T0 is clearly smaller than T1, I mean S1. So you have to be careful when you're using shift in order to do multiply. But for the most part, you're not going to be dealing with numbers this big, at least for the course. But if you end up doing something like assembly programming for some application that needs to be highly optimized, then these are things that you would have to be thinking about. All right. So we also have this instruction for loading the upper immediates. It's because we only have a 16 bits immediate value, right? So if we want to load a full register worth of immediate values, we need to have this load upper immediates to fill the top 16. Back here. If we want to load into the upper immediate of T0, 255. 255 is just 8 zeros, 8 ones, right? And then the lower immediate is still zeros. And then if we have larger constants that we want to load, we can use 2 instructions to load a 32-bit constant into a register. So we load upper immediate first, right? So this upper immediate goes into the top 32 bits of T0. Then we can OR immediate to get the rest of the zeros here to be the immediate that we want it to be. And now we have T0 filled with the 32 bits immediate that we wanted. Okay, so this is your full question for today. If we want to load this number, so this 32-bit number into S1, what's another way that we could do this rather than with the OR? And your code, what is your code? 095. So do this on your own first. anyone still thinking about this one? So we're not at the threshold, so do talk to the people around you, discuss how you got to your answer, and change your answer. If you change
I think it's just that. The other thing would just be adding it to the same. You don't have the bits for instructions for immediate 32 bits. And the.
Oh, wait, right.
Adding it to the same spot, so it's not the upper. And then.
Yeah,
I was thinking just adding.
It's like a good.
Yes. That instruction is too many bits to.
And do change your answer if you were convinced to change your answer. That's some movement, but not a whole lot. So let's go over this together. Okay, so let's start with A, right? So load upper immediate is going to take the register S1, put this 16 bits number in the top 16 bits and zeros in the bottom 16 bits, right?
Yes.
So we have the top 16 bits covered, right? Then we have add immediate. S1 is our destination. S1 is our other operand. So S1 is this 0x1, 2, 3, 4 with the top 16 bits. And then this immediate, it's
16.
so we fill it up with the bottom 16. And then we add them, right? And then 0 plus F678 is F678. So then we have 1, 2, 3, 4, F678. But I'm sorry to say that this isn't quite right.
No.
So one thing you have to remember about add immediate, there's no sub, right?
There's no what?
There's no sub immediate because add immediate gets sign extended. So this is a negative number, right? First bit is a 1, so we know it's negative. Because F is 1, 1, 1, right? So really what happens here is you have S1, which has 1, 2, 3, 4, and then 16 zeros. But then the add immediate sign extends this number to be 32 bits. And because it's negative, it becomes all ones in the upper. So it really messes up this upper part. So A doesn't work. And then the load upper immediate here, we already know this doesn't work, right? We're putting the wrong bits in the upper. And then add immediate here. What's wrong with it?
Too big.
The immediate is too big, right? We can only support 16 bits here. This doesn't work. So let's see this. So add immediate, S1, 0. This is putting, and this one is actually a positive number. So it doesn't get sign extended. So
For the same
this gets you 1, 2, 3, 4 in the bottom bits. And then it's adding F6, 7, 8 also to the bottom bits, but we're also getting the ones again extended. So really none of these. So I forgot to change E to But if you chose A, like that's the closest.
Okay. Sweet.
Yeah, I'll try and remember to change the slides after this. As I was explaining it, I forgot. This was time.
So because it's adding, all of those become 32 bits?
Yeah, they all get sign extend.
Okay,
Because in order for it to go into the ALU, which is expecting 32 bits, it's going to be sign extend.
So what would the correct code look like for this to add that hexadecimal into the register?
Do this.
Oh, you'd have to do the load though, or?
Yeah.
Okay.
Yeah, so you load upper and then you OR. Yeah, so this is the last line. So you have reading and for the last question, just answer anything on the poll. And I'll stick around if you have questions. So, 3.45.
Sorry for leading you guys astray. That was on me.
Yeah, we don't.
The map. Different actions. And
You were here and you answered.
Pretty, especially.